hear me? السلام عليكم ورحمة الله وبركاته. أريد أن أشكر MBRS بدعوتي هنا. أنا متشرف وفرحان ومسرور بزاف بهذه الدعوة. Thank you so much. راح نتكلم باللغة الإنجليزية لأنني عندي ممكن 30 سنة وندير العلوم باللغة الإنجليزية. سامحوني نتكلم باللغة الإنجليزية اليوم. I'm very pleased to be here. I'm really happy to share with you some of the work we've been doing. And also, I want to thank one more time the people who invited me here and thank the Space Center here in the UAU for their invitation and for this great conference. So, today I'm going to talk to you about some of the work that we're doing on Mars mission, but also I would like to connect the work that we do both for the Mars mission and for something on cancer. And although these two fields seem to be very distinct from one another, I hope I can convince you that science and technology are connected, and if you can find those connections, then the impact of our work is even greater. So, let me tell you a little bit about what I've been talking about. I'll go a little bit fast. But first I will describe to you the science goals of the mission, Curiosity mission. Then I'll describe one of the instruments, the chemistry camera. Then I'll talk about some of the techniques that we're using for the chemistry camera, very briefly. But then also I will talk about how we apply some of those approaches to fight cancer, in particular for detecting it very early. And then I would like to spend maybe a minute to look into the future. So the scientific goals of the mission are listed over there. This is the NASA Mars Science Laboratory mission. The scientific goals, so the overall goals, first is to assess Mars' biological potential by searching for features that may record the actions of biological processes. And we can talk about that if you want later on. Second is to characterize the geology of the landing site around the Curiosity rover, wherever we land. Also, another goal, scientific goal, is to investigate the processes that may indicate past habitability. There's a difference between past habitability and habitable today. And we will also characterize, one of the goals is to characterize also the environment of Mars. Because actually, that will tell us something about the human potential for habitability on Mars. And I would like to mention here that the scientific goal here is not to look for Mars for life per se, or habitability per se, but to look for the elements of habitability. So water clearly is a key element for habitability, so we'll talk about that. And anything that is hydrated also is clearly going to play a key role. So if you're interested, you can find these two articles, one in Science, and one also that we've looked in Optics and Photonics News in 2013, that describes some of these goals. Now the NASA's Curiosity mission is, if you can see here, we've got 3 rovers, and the Curiosity mission on the right-hand side, is clearly much bigger than the previous rovers that we had. And the reason it's bigger, because the goals, the scientific goals, require much more instruments than in the past. So for the Curiosity rover, we have about 10 instruments. So the 10 instruments, I'm not going to describe all of them because I don't have the time, but I will tell you that, grossly speaking, we've got 3 types of instruments. First, remote sensing instruments. Instruments that actually check about the distance of 1 to 7 meters, 1.6 meters to 7 meters, what we might be interested in. Second, some contact instruments that require the rover to move to the place and contact and touch the sample or the target that we might be interested in. Third, if there is a real interest, is actually to get some samples, bring them to the rover and do some study. So, as I said, I will be talking about principally one instrument, the chemistry camera instrument, called ChemCam. Let me give you at least a basic principle of how this instrument works. The instrument has two features that are important. One, it uses a laser. It's over there. It hits with a laser, we hit the target, the sample, a rock or a soil or anything that we're interested in. And the intensity of the laser is such that it ablates, it creates a vapor, so it vaporizes the element and it creates a plasma. That plasma then is the light emitted by that plasma is collected by a spectrophotometer, and then we get these signatures called spectra. So a little bit, these spectra are very, very important, and we'll talk a little bit about them in a minute. But the key thing to know is that every element, so every lot of different rocks and even metals, have different plasmas. And as a result, if you know what the plasma is, we might know what element it is. So here's how it works. So when we see a plasma, so when we see this plasma being formed, then we have an instrument that actually, just like a rainbow, gets that light and spreads it around into its components. And then, from there, from every component, we do know, I'll show you that in a second, what that light comes from, because the atomic structure of these elements tells us, the physics tells us, where is the element that is giving rise to those colors. Then we would know, for example, in this case, if it has potassium or sodium or whatever it might be. And the strength of those lines that we see, or the brightness of the light that we see, tells us something about how much of those elements we have. So, in 2008, my group published this database that was funded by NASA, by DOD, and by other agencies, NSF also. And we wanted to see whether each element, under some very peculiar environment, we can actually identify them, or whether they can all get merged. And the answer is we can. So essentially, to give you one example, here, one of my students, in 2006, Steve, we were asked to identify an artifact that was strange and we didn't know what it was. So we compared it to our database, this becomes a database, and we saw that it was mostly iron. You see that they are overlapped. So this is one way to use this. This is just one way. And it could be an artifact, it could be soil, it could be liquid, it could be anything. So, in reality, curiosity works this way. This here is the ChemCam, the chemistry camera. So you've got a laser in there that operates in the infrared and hits a target. The target looks like this. It has also a camera there called remote micro-imager that takes a photograph of the target that we want to hit. As it does, you can see it there, then we create a plasma, and once the plasma is created, light from the plasma is collected, so it goes back to, is collected by a telescope here, which goes then to a spectrophotometer, like I just said, and then at the end of the day, what we've done, this is before and after, we have dug into the target some holes. Because the laser is so intense, these holes, each of those holes is about 400 microns in diameter and about 50 shots in there. So, and then, looking at from the spectrophotometer, just like I just showed you that example, we can figure out what elements we have. Here, for example, we see that we've got some titanium, some manganese, and it could be other things as well. This is just an example. So that's how it works. If there's anything you can take from curiosity today's talk, is to understand that by using a very, very intense laser, and we can define what very, very intense means, we can actually get essentially a fingerprint of the target that we're using. Just like each of us, human beings, we have a particular and specific and unique fingerprint, so do the rocks and soils and dust and so forth. So, what are some of the results that we have? Well, some of the results that we have are here. This is one of the first spectrum that we have obtained, I think 13 days after landing. And what you can see is that in this spectrum here, we could already see how rich we got all these elements, titanium, iron, aluminum, silicon, etc., etc. But also, if you look carefully, there's the presence of hydrogen in this rock. In fact, a few years later, or a few months later, we actually did some more measurements and we found more and more hydrogen with the ratio of oxygen and so forth, which with the other instrument combined got us to the result or to the conclusion that we have shown that there is water on Mars that is ubiquitous, that exists on the planet. Now, we have also other results. This is a picture here taken by the remote imager of ChemCam, and you can see, we see what we call veins here in these rocks. When on Earth, we can see that too. So we have tried to look into what is this white stuff here. And what it is, in fact, when you look, it's quite complex to look in there because, because it's very, very thin. It's about 3 millimeters here thick. So what we find here is we found the elements of calcium and sulfur and hydrogen, and this proves also, again, that we have calcium sulfates. And these deposits here are also an indication of the presence of water. It is it's the same thing as when we are in my kitchen, for example, when water runs through tubes of lead or anything like that. After a while, you get these calcium deposits, and here it is a sign also that water went from here at one point during the history and the life of this mission. But from a technological point of view, you can see how difficult it is. If you look in here, we have a hole here, this was drill a hole, and we saw a vein, you can see it there, and there's another vein there. And the key thing is to orient the laser, focus it there, take a shot, and get the picture. That, only a laser can do that, and we've done it, and we've done it with great success. So this is, again, another great result of the ChemCam, and then many other results I'm not going to have time to share about. Another thing that we have also is on Mars, on Curiosity Rover, we have what we call calibration targets. These are targets built here in the laboratories, flown to Mars, and they have various glasses and various types of rocks and so forth. 5, for example, is a carbon graphite. It's just graphite. So the question was at one point also, can we simulate and calculate the spectra that we would see on Mars once on Mars? So from time to time we shoot at these calibration targets and get those spectra, get those those atomic and signatures, and this is what we get. So this is in red here. You can see this is what we've measured, and this simulation. What we've measured is the inserts here. You can see them there. And here are the simulations that we have. And now we have calculated, and we have an excellent agreement between the simulated spectra and those measured on Mars by Curiosity. And the reason we've been able to do that, because we characterized the environment very, very well, both in terms of pressure, environment, and in terms also of gases that exist. And so we know exactly what the intensities of the laser are, so we've been able to do this quite well. And that is also very encouraging, because it allows us now to simulate what we might see prior to shooting a target. So, how is this related to cancer? So, one of the things I haven't talked to you about is to classify. In what we do here also on Mars, we get these targets, and I showed you, for example, for a simple artifact that had iron in it. Great. But if it is a lot complex, if something is very, very complex, you need databases that are very, very large to know what type of rock you have. So you need to compare a target to a very large database. And we do that. We've developed some machine learning tools, and those machine learning tools allow us to actually classify very well the rocks that we see on Mars. So, first let me tell you why there's an interest in cancer. Why I'm truly interested in cancer research. And the reason is very simple. I think we all know it. Cancer remains a lethal disease. It's a very old disease, but it remains a lethal disease. These numbers are old, but I can tell you they haven't changed that much. 7.6 million people worldwide died from cancer in 2008. And if you look at the American Cancer Society statistics, I've played this a little bit. You take all the numbers, so the lifetime probability of developing cancer, all sites, is 1 of every 2 men and 1 of every 3 women. So, if we take this into account, and let me put these numbers in perspective for you. So, here's a stadium where people are looking at a soccer game. If I take those numbers and I just put them in place, it really means that all of those people who are now in shadow, are hidden, will have or are likely to have cancer at one point. So, we need to fight this disease preferably by approaches that are minimally invasive, i.e. by approaches that are available to a lot of people. So, on the left-hand side here, I have what we do for the work on Mars. And on the right-hand side, I will do for cancer. يشرفني الترحيب بكم بصاحب السمو الشيخ محمد بن راشد المكتوم. شرفتنا بحضراتكم. وعدكم صحة. So, for cancer, as I just talked on Mars, we classify rocks and soils by looking at large databases. We will do the same here. But here, again, let's just assume we can check the state of health of someone by comparing groups of people or groups of samples to a very, very large database. And I'll tell you that in a minute what that means. We're going to search for unique signatures for cancers. Very unique signatures for cancers. And we will have some imaging, just like we did on Mars, also for cancers. I will talk about that if I had time. So the motivation is there. The motivation is that we need to do this because there are also a key challenge in cancer is detecting it early. Most cancers, if they're detected early, they can be cured. If we don't detect them early, it's a lot harder. So, let me just give you this, will give you an idea. So when we are born, we're here, and time passes by, and all of us will go somewhere where we'll die, whether we want. So, on this side, we have organ integrity. We are healthy, and at one point, our organs start to give up. However, before they start to give up, there's something that is an onset to a disease. What is that onset to a disease? Unfortunately, too often, we go when that onset is past and we start to feel some pain, or we start to feel that we need to go to a doctor. So, let me go fast here. But here, it's prevention where we are healthy. We can look at genetic signatures. Today we can look at our genes and see what is the likelihood of somebody developing a cancer, or diabetes, or something else. And here we have clinical signatures. We really feel bad. We really feel maybe, something that the doctor can see. But in this area, where it really matters, we have signatures because those onsets start again sometime somewhere in the body. These will not be changed so much. We are born with those unless there's gene therapy in the future. Until that happens, this is our best chance, in my view, to actually detect early signs of cancers. The other thing I wanted to say is that disease is not a state, it's a process. So it changes with time, and that's very important to remember. So in my lab, we have focused on using the technologies that we have developed for Mars, and the mathematical models that we developed for Mars for cancer, but one type of cancer, ovarian cancer. And the reason we have focused on this ovarian cancer is very simple. because 26,000 women only in the United States die from this disease. And the second thing is that this cancer, if detected early, it can be cured in 95% of the cases. So it's very important to detect it early. It's extremely important to detect it early. So again, we can develop technologies that are not accessible to people, and that is difficult. Who wants to do biopsy every day? Or we can develop technologies that are based and are minimally invasive. So what we're about to describe to you is based on studying, just like we study rocks on Mars, the blood of people or saliva of people. And the work I'm going to describe to you is first in mice. The mice here are developed at the Fox Chase Cancer Center in Philadelphia. And these mice, technology has been developed there, we can actually trigger ovarian cancer in one of the mice. And in fact, we don't even know whether it's going to be the left ovary or the right ovary that will have cancer. So this is a controlled experiment where we know what these mice are going to have and when they will have that cancer. The problem is, if you have to wait until this volume of the ovary is up by 30 to 40% for the MRI to see it. The question for us, can we see it way before? Hopefully, when the first cell triggers that biomarker. That's the hope, the first cell. So we do that. I don't have time to give you the details, but here, these are blood from mice. And this is about 1 drop of blood for every mice, 1 single drop. And on a single drop of blood, we can do 1,600 measurements with laser. 1 pulse at a time. 1 pulse takes about less than a second to do the measurement. So, when we do all of that, this is the lab, but don't worry about it, we get the same signatures as we have for Mars. We get essentially, again, the atoms that exist in the blood. We know we have sodium, we know we have potassium, we know we have this and that. The question is, if I look at some of these digital signatures of the blood, what we can see that in some cases, here for example it's from cancer, and this is not from cancer. They are almost always the same. Almost always the same. But almost is not good enough. Because they have differences that we can find with models, mathematical models that we developed for Mars, that again I don't have time to go through, but those models we apply here now. So, this is what happens. These are 8 weeks old mice. Remember, some of them are going to have cancer, some of them will not. And at this age, these mice you cannot see by MRI or by any other means whether they have cancer or not. And remember, this is the result of a single drop of blood, measurement of a single drop of blood. And what we have, we just published these results. What we have here in red, doesn't matter. In red, for example, is cancer, and in blue is non-cancer. You can see there is some differentiation between the two. And if I go with 12 weeks, etc., etc., we can do that. And we have done this in mice with 75 to 80% accuracy blind tests. I.e., people send us blood from these mice, tell us, are they cancerous or not? If you just play a game, you get 50-50, right? But we get about 80% results which are very encouraging. We did it with the Sloan Kettering Center in New York for melanoma. Melanoma also is a deadly disease, and it's difficult to detect. So that's why we worked on this one too. And what we've got there, also blind test, is we got some tissues and blood samples. We did those signatures, atomic and molecular signatures, again, as I just showed you. I don't have time to show you all of those. And then we did the classification, 80% accuracy. We just did with prostate, about 85 accuracy. And now we're trying to improve all of those. And again, these are mice that have melanoma, and this is naive, so it's not, it's healthy. And again, using the technology that we have developed on Mars, this laser-induced breakdown spectroscopy, and the mathematical model that we developed for Mars with my colleagues, we are able to get pretty good results. Then, let's say we know that a mice must have cancer or might have cancer. The answer is, what we do there, is that we can actually tag, what we call tagging, with nanoparticles and follow that almost on an hourly basis or daily basis, because again, it's quite simple. Now, let me say this to the youth here. This work that we are doing, that I just presented to you, as biology in it, physics, chemistry, mathematics, STEM, science, technology, engineering, you are the future. It is yours. It is so exciting, and you can do it. You can do a wonderful job. Follow your dreams. Follow this. And I can show you what I believe medicine in the future would be. We will be looking at some space like this where we say people we need to follow and people who are healthy. And then we can track them down in time, maybe every 2 days, maybe every 3 days, because the saliva would work too. So that's the way I see the future of medicine. So now, your contribution, the youth here, the young students, please, your contribution to this or to any other STEM field. You have shown you before that 40%, not a little bit less than 30% of the people in the world are likely to develop cancers in their lifetime. I want you to take this challenge because you can and get that to be reduced to maybe 1%. And by the time you get up, not to exist. You will be part of the fight against cancer, and I know you can do it, and I know you will be able, then we will be able to have and contribute to humanity in a big, big way against a disease that kills about 8 million people. Stay tuned for March 2020. I don't have time to talk about that, but I just want to give you a few words to the students again. I want you to realize that as humans, we have the amazing ability to shape our future and change our lives and the world around us. It all starts with a dream. You did you had a dream for space. Success is not final. Failure is not fatal. It is the courage to continue that counts. This is from Winston Churchill. And here, I love this. I love this painting. I saw it in Istanbul. I know they said, don't take pictures. I took pictures. I loved it. Because what does it show? It shows people who are organized, going somewhere. They know where they're going. They have built a sustainable, a very, very heavy and sustainable bridge to go to their future. And they're going as a team. They're going as a family. They're going as a community. And that is wonderful. I love that. I took a picture and I keep showing it to my kids. They're sick of it. I keep showing it to them. Let me just tell you that about, somebody said here earlier on, about 1,000 years ago, a guy called Ibn Haytham, not far from here. He is. You know what he said? The seeker after truth is not one who studies the writings of ancient and following his natural disposition puts his trust in them, but the one who submits to argument and demonstration, and not to the sayings of human beings whose nature is fraught with all kinds of imperfection and deficiency. This is Ibn Haytham about 1,000 years ago, when we had our golden age. You know who is, by definition, what that makes him? Makes him the first scientist on Earth. That's the definition of science. Okay? He is, for me and for a lot of my colleagues, the first scientist. So, and in fact, he said a few things that I again will say. One last thought. I love these things too. Excellence is never an accident. It is always the result of high intention, sincere effort, and intelligent execution. It represents the wise choice of many alternatives. Choice, not chance, determines your destiny. That's Aristotle. And when it comes to the future, there are 3 types of people. Those who let it happen, those who make it happen, and those who wonder what happened. I hope you are those who make it happen. And my word for you is, have a dream. Work very hard at it. You can try to do always better, because at the end, that is what you feel is, you get the sense of accomplishment. By being part, and I really mean this, of the Mohammed bin Rashid Space Center, you students, or by being part of science and technology, you are already making history, and I want to congratulate you on that. Thank you. I want to dedicate this to all cancer victims and all cancer patients in the world. Thank you so much.